So hopefully we can move through this bit pretty quickly. I'm just going to give you a quick review of positional number systems, okay? Just because it's important, I know you all did this probably at the very beginning of your degree, but it's important to have it fresh in your mind. So quickly, I'm going to go through this. There are some examples to be done. I expect you to do them. I will pick on people randomly and ask them to come and tell me what the answer is. So, positional value systems, we know, for example, binary, decimal, octal, hexadecimal, where the position of a digit tells you the value of that digit. So the value of any digit depends on its position relative to some reference point. In decimal systems, we're all well aware that the decimal point is our reference point. Just in case you'd forgotten what the decimal system looks like, there is a quick reminder here. We use symbols 0 to 9. It repeats in blocks of 10. Any leading zeros, for example, are normally suppressed. However, in electronic representation, we need blank positions to be padded with zeros so that our numbers still make sense. Our leftmost column in our example represents 10 to the power of 2. The middle column is 10 to the 1. And the rightmost column is 10 to the 0. Yes? We're all very familiar with decimal. Agreed? Good. Anyone not familiar with decimal? Fabulous. So a decimal number example, if we consider the decimal number 2745.214, it can be written to the base 10 to remind us, if we're using multiple number bases, exactly what number base we're using, to emphasize that it's a base 10 number. So the decimal point marks the transition between positive indices and negative indices for powers of 10. Binary number systems. Binary is also a positional number system. However, our numbers increase or decrease in powers of 2. So what's the decimal equivalent of that binary number? Who can tell me? We've got about 1 minute to work it out, and then I'm going to pick on someone to come and tell me what the answer is. Is he right? Yeah. Great man. So, binary to decimal conversion and decimal to binary conversion, I hope you all know. So, binary to decimal, we just did. Does anyone want me to go through it? Speak now or forever hold your peace. If you don't know how to convert that, if you didn't know how to convert that binary number to a decimal number and you want me to explain it now, I will do it. Okay. I expect 100% in the exam for that question. Right, decimal to binary conversion. We just use the reverse of binary to decimal conversion, which is repeated division. Okay. So we express our decimal number in powers of 2 and write ones and zeros in appropriate bit positions. Do we remember how to do decimal to binary conversion? Yes, good. Can we all please have a go at 110012? Oh, I've given you the answer. That's too easy. Okay, I shall just quickly work through this one with you then to show you how it's done. So, if we have 25 and we want to write it in binary, we can say 25 divided by 2 is 12 plus remainder 1. 12 divided by 2 is 6 plus remainder 0. 6 divided by 2 is 3 plus remainder 0. 3 divided by 2 is 1 plus remainder 1. Half is 0 plus remainder 1. Okay? And that's our binary conversion, least significant bit to most significant bit, by using repeated division by 2. Yes? How? Okay, decimal to binary conversion. What's this one? You have 1 minute. And then I will pick on someone. 0.25 to the base 10 expressed as a binary fraction. Okay, that was 1 minute. Any volunteers from the female side of the class? Guys, say talk, please. You right? Well done. Thank you. Would anyone like me to show you how she worked that out? Would anyone like her to show you how she worked it out? Okay. Okay? Well done. Thank you. So a refresher on binary terminology. A single binary digit is called what? One binary digit is a bit. 8 binary digits is a byte. 4 binary digits is a nibble. Okay? Collections of bytes are known as words. We know that, right? You can have a 16-bit word, an 8-bit word, a 32-bit word. Octal number systems. So we use base 8 for octal rather than base 10, which we use for decimal, or base 2 for binary. Our digits in the range 0 to 7. So we have 8 digits in total. And decimal to octal conversion can be achieved using the now familiar method of repeated division, but using 8 instead of 10 as the divisor. Right. Octal to binary equivalent. Do we remember how to do easy octal to binary conversion? I hope you guys at the back do, because I'm going to choose someone from the back 4 rows for the next example. You've got 1 minute starting now. Okay, our next volunteer. Very simple, each octal digit can be translated exactly into 3 binary digits. So an octal value of 0 is simply 3 zeros. An octal value of 1 is a binary value of 0, 0, 1. Okay? Because we can represent 7 in 3 bits in binary, the octal to binary conversion is very, very simple. It's just 3 binary digits per octal number that exactly represents that number in binary. Okay? Thank you. That's yours, yeah. Well done. So 472 in binary is 100 111 010. Yes? Final to octal conversion. Just as simple. 11. Okay. But now every 3 digits in binary can be converted into a single octal digit. Starting at the decimal point, we can group in 3s, going left or going right. So we're missing a binary digit there. So this becomes 326.6 to the base 8. Simple. Yes? Hexadecimal. Uses base 16. We now have to have 16 different digits. There aren't 16 different single character numbers, so we have to start using letters as well. We use the letters A through to F to mean numbers 10, 11, 12, 13, 14, and 15 to give us 16 digits in total. to convert from hexadecimal to decimal, we can still use the repeated division method, but this time we have to divide by 16. Who's good at dividing by 16? I hope some of you are. So it's going to be, that was a lady, it's going to be a guy from somewhere around the middle on this side this time. You have 1 minute to convert that number to decimal, please. Okay, is that the correct answer? No, why? It's the correct binary answer, it's not the correct decimal answer. That's okay, you just made... $687 to the base 10. Does everyone understand how I got that answer? Yes? So hex to binary is fairly easy. Every hexadecimal character represents 4 binary characters. So we can simply go through, as we did with octal, assigning a 4-bit binary value to each hexadecimal character. Oops. Yes? So our example here of 2F5A to binary, which our friend already did for us earlier. Perhaps he was psychic. Okay? Do you have a lecture after this? Do I have to let you go at 20 past, or can I go until half past? Which one? Can I carry on, or? Right. Okay, so I'm going to carry on until 5:30 because you've got nowhere else to go apart from to dinner. So binary to hex conversion is still pretty easy. We simply have to split our binary into 4-bit nibbles from the decimal point outwards, and then pad it with zeros if necessary. So if this is our binary number, guys, please don't talk. My first lecture today was at 8 a.m., so I'm pretty tired of shouting. So we start at the decimal point and we segment our number into 4-bit nibbles and pad with zeros where necessary. Yes? To get simply 8. All right? Right, how do we represent a signed number in binary? Who can remember? Do we remember beloved 2's complement? Done 2's complement, right? Yes? No? Has anyone done 2's complement here? Has anyone never done 2's complement? Really? Tentama. Okay. So I probably wouldn't be asking someone to do the next example then. All right. You've really not done 2's complement in digital circuit design. Okay. So I'll slow down a bit then, because 2's complement is important. We need, of course, to be able to represent both signed and unsigned, positive and negative numbers in binary. Yes? There are 2 ways that we can do it. We can either use the most significant bit as a sign bit, which is not that one, So, right, okay. Let's take a small step backwards, and I'm going to introduce a new table, 3-bit signed using a sign bit. So for a 3-bit number, if we're using the sign bit method of representing negative and positive numbers, the sign bit is the most significant bit. And a 1 indicates a negative number, and a 0 indicates a positive number. And we can then just progress with normal binary. So -4 would be 1. No, we can't. Sorry. -3 is 1, 1, 1. -2 would be 1, 1, 0. -1 would be 1, 0, 1. 0 is always 0. +1 is 0, 0, 1. +2 is 0, 1, 0. +3 is 0, 1, 1. Okay? So the most significant bit is our sign bit, and if our sign bit is 0, we have a positive number, and our sign bit is 1, we have a negative number. Yes? Have you seen that shorthand before for positive and negative? Okay. Westerners are lazy, and rather than writing positive and negative all the time, for positive we write plus BE, positive. So the VE is the end of positive, and negative we'll write minus VE. Again, the VE comes from the end of negative. Okay? So it's a shorthand notation so that we don't have to write positive and negative all the time. Okay? So the sign bit is the most significant bit, and it tells us whether our number is positive or negative. So a 0 means we have a positive number, and a 1 in the most significant bit, which means we have a negative number. And then the final 2 binary bits simply represent the number itself. Yes? Yes. Pardon? Good question. What's 100? They're both zeros. So, several slides in the future. Excellent question. It's not true that everyone at the back is asleep. We don't use that method because we end up with a positive and a negative 0. And we've wasted one of our states. Okay? So we don't use the sign bit and then just the final binary digits to represent the exact number, because then we end up with a +0 and a -0. And we've wasted a state. What we use instead is something called 2's complement. Which looks like we're just using a sign bit for the positive numbers. Yes? So this set of numbers looks the same as this set of numbers. The most significant bit is 0, showing us we have a positive number, and then the final 2 binary digits simply represent the value of the number itself. Right? However, when we come to negative numbers, it's all very different. -1, all the bits are high, all the bits are 1. -2, 110. -3, 101. -4, 100. We still and look at the sign bit to know the sign, the most significant bit, so that we have a negative number. But the final two bits no longer tell us the value of our number, right? This is not 3, this is 1. This is not, this is 2. Okay? Because it's a system called 2's complement. So, I'm going to, I've still got a few minutes, so we should be able to finish 2's complement. So why would we use 2's complement? Well, it seems like a unnecessarily convoluted system. I'll show you how to convert a binary number to 2's complement binary number in just a moment. I'm going to tell you first why we bother. First reason, we don't want to waste a state. We don't want a plus and minus 0, right? Because they both mean the same thing. They both mean 0. Also, a CPU or an ALU doesn't ever actually do a subtraction. You will find this out in the lab when you design your ALU. ALUs only add. They pretend to do subtraction by adding a negative number, by adding a 2's complement negative number. Okay? So rather than doing 6 minus 3, what they would actually do is 6 plus minus 3, where this number is in 2's complement. This means that our ALUs are significantly simpler to design because they only have to do addition. They don't actually have to do subtraction. So this keeps our arithmetic operations consistent for both sides. Okay? So I'll show you how to convert to 2's complement now, and then tomorrow we'll do some examples of 2's complement, addition and subtraction, and so on. So for any binary value minus a, the 2's complement value is simply 2 to the n, where n is the number of bits that we have, minus a. All right? The simplest way to convert a number from a positive number to its 2's complement, so to convert from 3 to minus 3 or from 6 to minus 6, is to invert all the bits and then add 1. For example, someone give me a 4-bit binary number. Anyone? No one? Okay, what's that? What's that in decimal? 0110 is 6. Let's say we want minus 6 is what? In 2's complement? First of all, flip your bits. 1001, okay? Flip means to turn something the other way up. It means to invert. All right? And then add 1. So 1010 is minus 6 in 2's complement. And you can see that the sign bit, because we flipped, the sign bit has now changed from positive 0 to a negative 1. Okay? And that's all you have to do to convert to 2's complement representation. So let's go for 1 plus 1. What's minus 1? Did anyone tell me what minus 1 is in 2's complement? You've got about 1 minute to figure it out. Just split the bits and add 1. My final bit for today. Okay, is he right? and I'll see you all tomorrow.